The next two sections I grouped together because they're both about related rates. One is about calculating related rates, and the other one is about interpreting what a related rate is. So related rates are when you have a situation where more than one variable is changing with respect to time. So for example, as this guy blows up his balloon, the radius of the balloon is changing over time. The volume of air in the balloon is changing over time. And the surface area of the balloon is also changing over time. So those are all related to each other. The surface area will increase faster if the radius increases faster, but they aren't all identical. Or if you have a conical cup like they serve at the dentist office, those little paper cups, and you go up to the water cooler and you fill it up with water, the radius of the water is changing over time, although the cup doesn't change radius. The volume in water is changing over time, and the height of the water is changing over time as you fill up the cup. Or let's say you have an unfortunate accident with your ladder and your ladder slides down a wall. The height of the top of the ladder changes over time, and so does the bottom of the ladder. That changes over time as the bottom gets farther away from the house. And even the angle that the ladder makes with the ground over time changes. So those are all related rates because they all change with respect to time. If you're flying a kite, the height of the kite can change with respect to time. So can the length of string that you let out, and the angle that the kite makes with the ground could change with respect to time. Those are all related rates because they affect each other, but they're not all the same rate. We're going to do an example together, and this is on your note sheet if you are using my note sheets. The radius of a circle is increasing at a rate of 2 inches per minute. Find the rate of change of the area when the radius of the circle is 6 inches. I use a graphic organizer when I do these. Use a foursquare. You don't have to, but in the middle of the foursquare, I try to figure out what am I trying to find out. So I am trying to find the rate of change of the area when the radius of the circle is 6 inches. So I am trying to find dA dt, which is the change in area over time. That's the rate of change of the area. Then I draw a picture of the situation, if it's applicable. So here's a circle. In my picture, everything that is changing should be labeled with a variable because it's varying. So in this particular example, the radius is r. There is a point when the radius of the circle is 6 inches, but the radius is increasing. So we're going to put an r there. For a circle, that's really all the only measurement we have for a circle. Then there's a relationship, and the relationship is between what we're trying to find, area, and radius. And so often that's an equation, might be two equations, but in this case, because it's a circle, the area is pi times the radius squared. And then we do some calculus, and we're doing calculus on this relationship that we have between the radius and the area. So we're going to take the derivative of both sides. But we are going to take the derivative of both sides with respect to time, which means we have to treat every single variable as kind of the way we were treating y coordinates. Because the derivative of a with respect to time is dA dt. The derivative of r with respect to time is dr dt. So as we're doing this problem, we need to make sure that we treat all of our variables like they're functions of time. So the derivative of a would be dA dt. On the other side of the equal sign, we have 2 times pi times r to the 1 power times, now we're going to use the chain rule because r is a function of time as well, times dr dt. I want to point out just a really cool relationship here. When we took the derivative of the area of a circle, we got the circumference of the circle. Isn't that cool? All right. So then the last step is to plug and chug. So in this box, we are going to fill in for any variables that we have information about. We're trying to find the rate of change of the area when the radius is 6. So we're going to use dA dt is equal to 2 pi r, but r is 6, and the radius is increasing at a rate of 2 inches per minute. For kicks, and because Mr. Roddy really likes units, I'm going to put some units in here. So this is 6 inches for the radius, and the rate of change in the radius would be 2 inches per minute. When I multiply this all out, I get 6 times 2 is 12, times another 2 is 24 pi, and then I have inches squared per minute, which are units that totally make sense for change in area over change in time. We should have inches squared per minute. For these problems, you only need to use correct units when you are asked to use correct units, but make sure your units are correct. And it is helpful if you can make sure that you convince yourself that the units work out. All right, I'm going to use that same model for the second example. You don't have to use the model if it doesn't work for you, but I think it really helps keep everything straight in your mind. The volume of a spherical balloon is increasing at a rate of 3 inches cubed per minute. Find the rate of change of the radius when the radius is 10 inches. So what are we trying to find? We are trying to find the rate of change of the radius. So we are trying to find dr dt. This time it's a sphere, so I'm going to show that it's three-dimensional by making an equator around the sphere, and the radius is changing as I'm blowing up the balloon. The relationship is this equation that we were given, volume equals 4/3 pi r cubed. I just thought, that's one. I would expect you to know the area of a circle off the top of your head. Volume of a circle, I wouldn't expect you to know necessarily. We're going to do calculus on that relationship, so we're going to take the derivative of v, which is dv dt, equals 4/3 and pi are constants, so we can just leave those alone. And then we bring the 3 down in front, and we have r squared, but r is also a function of time, so we have dr dt. These 3's can cancel, so we have 4 pi r squared times dr dt. And did you notice that the derivative of the volume gave you the surface area of a sphere? What? All right, last step, we're going to plug and chug. This time the plug and chug is a little bit different because they gave us dv dt, so we're going to plug in 3 inches per minute, 3 inches cubed per minute. That's a dv dt measurement. So we're going to put 3 in for dv dt, so 3 equals 4 pi, our radius is 10 inches, times dr dt. We are trying to solve for dr dt. Luckily, we know algebra, so I'm not worried about it. It looks like we will get 400 pi. We'll divide to get dr dt by itself, so dr dt equals 3 divided by 400 pi. And I kind of got sloppy with units, but let's take a minute and think about units. The units for the radius would be inches, but we're squaring it, so that would be inches squared. The units for volume is inches cubed per minute. So when we divide this stuff, we'd be dividing inches cubed per minute divided by inches squared, so we'd wind up with inches per minute. Now, I'm going to do the rest of the examples on this video, but I actually recommend that you pause and try them yourself. All right, this one we're trying to find how fast the rocket is rising, so I'm going to call that a change in height over change in time. I'm going to draw a picture. Rocket is rising straight up. So here's my rocket. Here's some fire. From a level platform, I have an observer. My observer is standing here watching. And this is an example of a time when we are going to put a number on our diagram because the observer is not moving. So this 1,000 feet is a constant. But the rocket is shooting up in the air, so the height is changing. And then the other thing that's happening is the angle of elevation is changing, so I'm going to call that theta. Now, if I want a relationship between height and theta, I am going to use right triangle trig. Looks like tangent of theta is going to be h over 1,000. I'm going to take a derivative of this equation. The derivative of tangent is secant squared theta, but theta is changing with time as well. So that's going to be chain rule, so times d theta dt. And then I'm going to think of h over 1,000 as 1/1000th times h, so that I'm not doing quotient rule because it's a constant times h. So I have 1 over 1,000 times dh dt. Now I'm going to plug in some numbers. So I have secant squared when it's pi over 3. So secant of pi over 3 is 1 over cosine of pi over 3. And isn't cosine of pi over 3 a half? Yeah, so secant would be 2. So this would be 2 squared times d theta dt. Oh, we've got that 0.5. 1 over 1,000. And then dh dt is what we're trying to find. So we'll multiply both sides by 1,000. So we have 4 times, so 2,000 equals dh dt. Put a box around that. If I were looking for units, I would say feet per minute. Okay, 13-foot ladders leaning against a house. So we are trying to find the rate of change of the height of the ladder. So here's a picture. Here's the house. Here's a 13-foot ladder leaning against the house. The height is changing because the ladder is falling, and the base is changing as well. A relationship between the height and the base would be the Pythagorean theorem. B squared plus h squared equals 169. I strongly recommend you don't solve that for h. I strongly recommend you do your calculus at this point. If you do solve it for h, your calculus is going to involve a lot of chain rule, and it's going to be pretty ugly. But if I do it this way, I have the derivative of b squared, which would be 2b times db dt. Derivative of h squared, which would be 2h times dh dt, equals 0. Now we're going to plug and chug. This is an example of actually one where we might need to use this relationship in order to get a value. I'm going to divide both sides of this by 2 so that I don't have to deal with those 2's. So B, the base of the ladder, is 12 feet from the house, so 12 feet times dB dt. The base is moving at a rate of 5 feet per second, plus h, oh, we don't know h, but we can figure out h because b is 12, so we have 144 plus h squared equals 169, so h squared equals 25, so h must be 5. And dh dt is what we're trying to find. So if we subtract 60 and then divide by 5, well, 5 times dh dt equals 60. And so dh dt equals 12. And that would be measured in feet per second. All right, I'm going to stop here because I won't have time for the last example, but I will make a separate video. Thanks so much. Bye.